All right, let's try this again. I actually have a separate microphone, so you should be able to hear me half decently now. So, as I mentioned before, this problem is meant to be a reflection of what you saw of number 15, where you have a scenario with an applied force, a known angle, an acceleration given to you, but an unknown mass. So, just the quick on the information given on the board, you have the object. It has an acceleration of 4.30 meters per second squared. The coefficient of friction is 0.200. This is all because of an applied force of 350.0 newtons at an angle of 40.0 degrees. So I have the diagram all set up for you folks, very similar to what we've been doing all along this semester, looking at force due to gravity pointing down, normal force pointing up, force of friction opposing the motion, applied force at the angle of 40 degrees, and there's the x component to the applied force, and there's the y component to the applied force. Now these values in red, I calculate ahead of time. To get those, it's just taking the our trig ratios of sine and cos, dealing with the adjacent, opposite, and hypotenuse for that triangle. It's pretty straightforward stuff. I didn't waste any board space trying to show those calculations, but they are needed to solve the problem. Where this problem becomes unique is how we set up the sum of forces. So if we're to take a look at that line right there, that's showing that there are three forces in the y-axis. Normal force pointing up, applied force in the y-axis pointing up, and the force due to gravity pointing down. Those three forces are balanced. This is almost like a static situation where there's no acceleration in that y-axis. I'm not going to give you any acceleration in the y-axis problems unless we see something like an elevator. So since that's not the case here, we can assume they're balanced out and equal. So the sum of the two forces pointing up, Fay and Fn, they have to counterbalance what you see for Fg. So that's why that equation shows the two of them together is equal to Fg. Now what makes this different than what we've seen previously is that there's no vector notation. I'm not indicating direction by using positives or negatives. It is not dissimilar from what we've been dealing with force of friction all along, that the force of friction is an x-axis force, the normal force is a y-axis force, and that coefficient is just a coefficient. It doesn't have any values to it or any units to it. It just changes the value of the normal force. With this, we have never at any point this semester treated it like a vector. It's always been treated like scalars because you can use positive and negative if it's just the y-axis. You can use positive and negative if it's just the x-axis. But barring some sort of use of linear algebra, we can't combine them. And we're not dealing with linear algebra, so we have to do this in a slightly different way. So there's the y components, or the y forces. The x forces are up here. So again, it's the applied force in the x-axis. The force of friction is acting in the opposite direction, so it is Fax minus Ff, and that equals the net force in the x-axis. And that really is the net force for the entire problem because everything we see in the y-axis is all balanced out. So the only place for something to be not balanced, that is causing this acceleration of 4.30 meters per second squared, is from that combination of the applied force in the x and the force due to friction. So in the next line, instead of saying F net x, I say it's ma, and it could be max because that's where the acceleration is, in the x-axis. To combine these, because of the issue of not having enough information, not having enough knowns to solve for things like Fg, like normally we find that, but we don't have the mass. And without Fg, we can't find Fn. Without Fn, we can't find Ff. We're into those weird scenarios. So in this problem, what I'm going to do is to look for commonalities. And when we consider that the force due to friction, x-axis, is found by mu, coefficient of friction, times Fn, there's that y-axis. There's the thing that binds them together. So in this problem, instead of saying Ff, what I'm going to say is mu Fn, because that's what Ff is equal to. And then instead of saying Fn, I'm going to say what the normal force is actually equal to. So go back to this line we had originally, Fay plus Fn equals Fg. I'm going to rearrange this, bring the Fay to the right-hand side, subtract. So Fn equals Fg minus Fay. And then one further step, force due to gravity, I'm going to say what it actually is equal to for calculations. Mass times acceleration due to gravity. Mass of the object in kilograms, and acceleration due to gravity at 9.81 meters per second squared. There's that mass again. So we find mass here. We also find it here. So it's in two places, and we're going to have to combine those somehow. So what you see in the green box is that instead of calling it mu Fn for the friction, it's going to be mu times what Fn is equal to. What is Fn equal to? right here, Fn equals mg minus FAY. So I substitute that in there. So in the next line, the FAX is unchanged, minus mu, fine, that's the part we had right here, mu times Fn, but now it's times mg minus FAY. mg minus FAY. There's that substitution, equals MA. That part's unchanged. Next line, we're going to expand it, the stuff you're dealing with in your math class. Whenever you see parentheses or round brackets, or whatever you want to call them, it's the material on the outside multiplied by everything on the inside. So mu times mg, and it's a negative here, so it's negative mu mg, and then negative mu times negative FAY. So the double negatives gives us a positive mu FAY equals MA. So when I look to this part of the equation, I have FAX, I can calculate it, and I'll show you in a second. FAY, I can calculate it. I'm trying to find mass. I'm given that coefficient of friction. I know what the acceleration due to gravity is. There's a mass again, and there's the acceleration. I know the acceleration from what's given us in the problem. So this presents us with an equation that has the knowns that we need and only one unknown we're trying to calculate. So I want to combine my like terms. I want to take this, I want to solve for mass, solve for m, so that's what I'm going to do. I have MA, I'm going to bring this over by adding plus mu mg to that side, and I actually just flop the equations over, so what was on the right is now on the left and vice versa. So it's MA plus mu mg equals FAX plus mu FAN. There it is, or FAY, sorry. So there's the combined like terms. I factor it out because mass is here and mass is here. So now it's going to be m times a plus mu g. There's the mass. There's the thing I'm trying to find in this problem. It's brought into these parentheses, so now I can divide everything out. So it ends up being FAX plus mu FAY divided by a plus mu g. This kind of gross looking equation that we haven't seen before, but it all follows this flow, this logic of trying to manipulate the two equations to solve for that value of mass. But I plug in the value of FAX, which actually is 268.11 newtons. I didn't show that in the board. That's again that trig thing where this is the adjacent, there's a hypotenuse, so I'm using cos. That's the opposite, that's a hypotenuse, so I'm using sine. That part we should be good with now. That shouldn't be a problem for you to resolve a vector into its two components. So that value would be your FAX, 268.11, multiplied by mu 0.200 times our value of the FAY, 224.98. Acceleration, 4.30 meters second squared, plus mu 0.200 times 9.81 meters second squared. Not negative, this is all scalar stuff. No positive, negatives, just adding, subtracting where required for the equation. Plug that all in, I get 50 kilograms for the mass, and that is the solution to it. So this represents the exact way you approach number 15. It gives you the same kind of setup. I don't want you to skip right to here because it's important to know how to manipulate the equations in future problems, knowing they can take two sets of equations that talk with the same sort of variables like the normal force and combine them together into one single equation to solve our problem. So that's it.